Okay, so let's talk about the thickness of a given hyperplane. Remember, we're not even close to getting the fattest hyperplane. We just want to say, if you give me some random separating hyperplane, can I find its thickness? Can I find its thickness? Can I determine the thickness of the hyperplane? So determining the fatness or slash thickness of a separating hyperplane. Okay. Well, let's go back to this picture and remember that the thickness of the hyperplane corresponds to putting this cushion and expanding it until you hit the closest data point. So the thickness of the hyperplane is exactly the distance to the closest data point. So the thickness, and we typically call this the margin. Gamma of H. Remember what is H? H is a hyperplane, WP. So the margin, gamma of H, is equal to the distance from H to the closest data point. And that should jive with your intuition from that picture. You expand the cushion and you stop when you get to the closest data point, and that's the thickness. Well, it's twice that, but factor of 2, who cares about the factor of 2? Well, let's say we're finding the half distance or the half thickness. Okay, so what is the distance to the closest data point? It's the minimum over all my data points of the distance from xn to h. That's all that. I'm just rewriting the top line, which was English, now math speak. Okay, and we now have an expression for the distance. Bam. Okay, so this is the minimum over all my data points of the absolute value of W transpose xn plus b divided by the norm of W. Well, this norm of W doesn't depend on xn, so I can pull it outside the minimum. So this is equal to 1 over the norm of W, the minimum over your data points of W transpose xn plus b. Okay, now, can anybody tell me what this is? I'll give you a couple of seconds. Pause the video. I'll give you a few seconds. 1, 2, 3, 4, 5. Can anybody tell me what that number is? Well, you see something similar here? Okay. So, let's look at this guy. Okay. The minimum of my data points of yn W transpose xn plus b equals 1. But that means that each of these numbers is positive. Okay. So the minimum over n of yn W transpose xn plus b. Okay, this is equal to 1. But that's equal to the minimum over n of the magnitude of yn W transpose xn plus b. Okay, why? Because these guys are all positive. So a positive number equals its magnitude. And the magnitude of a product is the product of the magnitude. This is the minimum over n of yn W transpose xn plus b. And what's the magnitude of yn? That's one of the convenient things of making our yns plus or minus 1. So in some places you will see that people define classification as 0 or 1. Well, it's much more convenient to define it as plus or minus 1. Because the magnitude of this yn is now 1. So this is the minimum over my data points of W transpose xn plus b. And this is equal to 1. So now you see why it's so convenient that we sort of made a much more precise definition of what it means to separate the data. Okay, because it simplifies this expression considerably. It says that the thickness of a hyperplane, so this quantity is 1, because we're only interested in the thickness of a separating hyperplane, and a separating hyperplane satisfies this constraint through its definition. So the thickness of a separating hyperplane is equal to just 1 over the norm of the weights of the hyperplane. Very nice. So let me summarize that also here. So here we're building up a nice catalog. It's always nice to have a catalog. People like catalogs. You can order from them toys or whatever. But we're getting a set of very beautiful toys in our catalog. Okay, so the thickness of a hyperplane. So the thickness of a hyperplane. Okay, so gamma of h, and h depends on, w and b, and this thickness is sometimes called the margin. So you will hear people say the margin of a hyperplane is equal to 1 over the norm of the hyperplane's weights. Okay. Now I should be more specific of a separating hyperplane. Okay. And let's just pause a few seconds to just think about what does this depend on. And it looks suspiciously like the thickness of a hyperplane depends only on the weights of the hyperplane. The thickness depends on the weights. It's just 1 over the norm of the weights. So I want you to pause for a second and think, what else does it depend on? And this is very important. Okay. Even though it looks like it only depends on 1 over the norm of the weights, it depends on something else. 1, 2, 3, 4, 5. Well, if you're coming back and you just want to be here for the ride, remember, the thickness of a hyperplane also is defined with respect to a data set. If I had no data set, the thickness is infinity. I can just expand the cushion as much as I want. The reason the cushion is finite is because of the data set. So this guy depends on the data set as well as the weights. Okay. So where's the data set? It looks like the data set has disappeared. Where's the data set? 1, 2, 3, 4, 5. If you're coming back and you figured it out, the data set is embedded in this notion of separating. Okay. And it's embedded in here. So these weights must satisfy a constraint, okay, that they separate the data. And so that's where the data comes in. So the data has a role to play in the weights. The data influences the weights. Okay. So now we have a precise sort of definition of what it means to separate the data, a convenient definition. It's not that what we had before was not precise. We know how to compute distances, and we have miraculously gotten a very simple expression for the fatness of a given hyperplane. Okay? And so, well, the task of finding the fattest hyperplane is to simply find the hyperplane with the largest margin that separates the data. So finding the fattest hyperplane means maximize 1 over the norm of the weights, subject to the constraint, subject to the fact that it separates the data. The minimum of your data points, what does it mean to separate the data? Yn W transpose Xn plus B equals 1. So, let me just massage this a little bit. Okay. Turns out that, so we're done. Well, let's massage this a little bit, okay, to put it in a much more convenient form. Now it's mathematical convenience, okay. We're conceptually done. Maximize 1 over the norm of the weights is equivalent to minimize the weights. Okay, so that's equivalent to, so this is equivalent to minimize the norm of the weights. Okay, so this is equivalent to minimize the norm of the weights. But if you're minimizing the norm of the weights, that's equivalent to minimizing the norm of the weights squared. Okay, and minimizing the norm of the weights squared is equivalent to minimizing half the norm of the weights squared. I can put a half here if I want. And so then it's equivalent to minimizing the norm of the weights squared, half the norm of the weights squared, which is equivalent to minimizing 1/2 W transpose W. So finding the fattest hyperplane is equivalent to the following now mathematical problem. Here we talked about, we can think about visually moving the hyperplane around until it has the largest thickness. That corresponds mathematically to the following optimization problem. Okay. So we have reduced the task to solving an optimization problem. This is an example of an optimization problem. Okay. And now let's massage this optimization problem a little bit to get it into its final form, and that's the form that is typically used. Okay, so let me erase this. Okay. So minimize 1/2 W transpose W subject to the min of over all your data points of Yn W transpose Xn plus B equals 1. Okay, well, certainly if this if the minimum is equal to 1, it means that, yn w transpose xn plus b is greater equal to 1. So we could consider an alternative optimization problem with this constraint. So minimize, 1/2 w transpose w subject to this inequality constraint where I replaced equals to 1 with greater equal to 1. Okay. Now, certainly, if you solve this problem, you have a solution to this problem. So the feasible set here is larger. But I claim that when you solve this problem, you will have solved this problem. So let's see why. So the only consideration is that what if all these values are strictly greater than 1? So there's no value that's equal to 1, making the minimum equal to 1. If there's no value that's equal to 1, they're all greater than 1. Okay, it means that I can shrink W and B and lower the values a little bit. If I can shrink W and B, I've lowered the norm of the weights. So then I'm not at an optimal for this problem. Okay. So I'm claiming, and now you can sit down and prove rigorously, that if you're at an optimal for this problem, it will necessarily be the case that one of these constraints will be saturated. And that means that the minimum will not only be greater equal to 1, it will be equal to 1. Okay. So these two are equivalent optimization problems. Okay. These constraints are not equivalent constraints, but these are equivalent optimization problems. What that means is that any solution to this problem, if you solve this problem, it will be a solution to this problem. It will be an optimal for this problem. If you solve this problem, it will be an optimal for that problem. But the feasible sets are different. And if you think about it, think about when we talked about regularization. The regularization constraint was W transpose W less equal to my budget C. And then we made the argument that, it suffices to only have to consider the situation W transpose W equals C. Okay. So there are many situations where you can expand the feasible set and make the optimization problem easier, okay, in the comfort of knowing that the solution will satisfy your original stricter constraint. Okay, so these are equivalent optimization problems. So it means that we can equivalently find the fattest, the maximum margin hyperplane by minimizing the norm of the weight squared, okay, with a half, minimize the norm of the weight squared subject to inequality constraints. Subject to yn w transpose xn plus b greater equal to 1. Now, why is this more convenient? Because we don't have the messy min. Okay, so we just have an independent constraint for each data point. So here, let me make some observations. What we're minimizing, so what do we have to choose? We have to choose w and b. So my variables in the optimization are W and B. Let's look at what we're minimizing. That's called the objective. The objective is quadratic. Okay. And the constraints in terms of W and B are linear inequality constraints. Linear inequality constraints. Okay. So this is a quadratic optimization problem with linear inequality constraints. This is an example of what is called a quadratic program. This is a quadratic program. Or sometimes we abbreviate it to QP. Okay, so let me erase. Okay. And let me show you how we solve this problem. At least let's do an example with that case. Let's find the optimal hyperplane, the fattest separating hyperplane for our little toy example. Okay. So it means that we have to solve this optimization problem. So what do we have to find? We have to find W1, W2, and B. Okay. And we have to minimize 1/2 times the norm of the weights. So we have to minimize 1/2 W1 squared plus W2 squared. Okay. And we have several constraints to satisfy, one for each data point. So let's take the data points one by one. Okay, so for data point 1, this y is negative, so we have, and x is 0, so we have negative b greater equal to 1. Negative b greater equal to 1. Data point 2, this is negative, and now x1 and x2 are 2, so we have negative of 2x1 plus, 2w1 plus 2w2. So this is W transpose X, where both of the components of X are 2 and 2. okay, plus b is greater or equal to 1. Okay. And then the other two data points, y is plus 1, so we have, x2 is 0, so we only get w1 coming in, so we have 2w1 plus b greater or equal to 1, and 3w1 plus b greater or equal to 1. So these four constraints are exactly all these constraints. Okay, so these constraints must apply for n equals 1, 2, up to big N. Okay, so let's solve. Well, if you solve, let's see, if you add this and this, the b's cancel, so you get 2w1 greater or equal to 2. This implies w1 greater or equal to 1. If you add this and this, then we get that the two w1s cancel, the b's cancel, so we get minus 2w2 greater or equal to 2. This implies that w2 less equal to minus 1. Okay. So since we're trying to minimize the norm, we want to choose the magnitude of the w's as small as possible. The smallest you can choose is w1 equals 1 and w2 equals minus 1. And it turns out that you can satisfy all these constraints with also choosing b equals to minus 1. Okay. So b equals to minus 1 is a solution. And so we've got our weights and our bias. So sine, so h of x, h optimal, so fattest, h fattest of x is equal to the sine of w1 x1, which is x1, minus plus w2 x2, which is minus x2, plus b, which is minus 1. Okay. So that's not optimal. It turns out that optimal has to rotate a little bit. So let me draw for you what optimal looks like. Optimal is something like this. And the thickness of the hyperplane is 1 over the norm of the weights. The weights are 1 and 1, so the thickness 1 over the norm of the weights, which is the margin, is equal to 1 over root 2. So the thickness here is 1 over root 2, or 0.707, something like that. Okay, and the hyperplane is such that when you expand your cushion, it hits those two red points and it hits this blue point. Now, it should be obvious to you that it should hit a red point and a blue point simultaneously when you have the optimal hyperplane. Because let's say that there's room left on the blue side, then you can shift the hyperplane a little bit and expand. Okay? So the fattest hyperplane will always hit the red and the blue points simultaneously when you reach the maximum fatness. Okay? That's not true for a non-optimal hyperplane. Now, I'm going to box some data points here. It hits these guys simultaneously. So you can think of these data points that it hits simultaneously as we're expanding the cushion as supporting data points. They are what prevents it from expanding more. So these data points are called supporting data points or support vectors. Support vectors. Okay. They are what prevent it from expanding more. I want to make another very important observation. It will be useful later. What about this guy here? So what about this data point? It's not a support vector. An interesting observation is if I threw that data point away, would my optimal hyperplane change? Okay, so let's see. I throw this data point away. Well, whatever the hyperplane that remains, and certainly separates the data that remains. Okay, because it was a separating data point when I didn't throw it away, and now that I threw it away, it cannot fail to separate the data. The only question is, now that I've thrown some data away, can I make it larger? No, because it's not one of the supporting points. So the optimal hyperplane will not change when I throw away this data point. And intuitively, you can look at this and say, well, that looks like a redundant data point. And indeed, it sort of is. So in order to define this optimal hyperplane, I only need to know what are my supporting vectors. Very interesting observation. To define / find the optimal / fattest or max margin hyperplane, it suffices to only have the support vectors. The other data are, in some sense, redundant. So all the information necessary for constructing the optimal, the most robust to noise hyperplane is embedded in the support vectors. So in an indirect way, okay, the optimal hyperplane identifies the important data point. So what a beautiful byproduct of this algorithm. Okay, Right. Okay, now, we are not going to solve by hand this problem every time we have a data set to sort of separate and find the fattest, most robust hyperplane. Okay? So we need an algorithm. We're not going to solve it by hand. And the good news is that the folks over on the mathematical side, in the optimization arena, have solved this problem beautifully for us. Okay? Using what is called quadratic programming. So we're not going to solve the quadratic programming problem. They have solved it. They have developed algorithms. We're going to use their algorithms for quadratic programming. So next, I'm going to tell you how we solve this problem on a much larger scale, where we can't solve it by inspection and manual algebra. Okay. So we'll come back. Let's talk about quadratic programming.